This is an example for a single condensable component for vapor-liquid equilibrium. In this case, we have liquid water in equilibrium with water vapor and air, and this is in a piston cylinder type system. So we start with the drawing. The idea is that we have a piston with a weight and liquid water in equilibrium with water vapor and air. The total pressure defined in the problem statement is 1.2 atmosphere. Since it is a piston and cylinder and we don't change the weight, that means we keep that pressure constant. We are also going to keep the temperature constant as specified in the problem. The question is, if we were to attach some kind of syringe and remove some of the air but no water vapor, what would happen in this system? So let's look at this from the viewpoint of using the ideal gas law and assuming vapor-liquid equilibrium. If we keep the temperature constant, then it means that the saturation pressure for water would not change, since it's just a function of temperature. We could calculate that using the Antoine equations. So we start out with the pressure of the water must be at Psat, because we're at vapor-liquid equilibrium, and there's no air in the water. When we remove some of the air, we decrease the gas phase volume, but we're keeping the total pressure constant. And the total pressure is the pressure of the air and the pressure of the water. Now we know the total pressure is 1.2 atmospheres, but we don't really know the values of these other numbers, but we could pick reasonable amounts based on their temperatures. And since we know the partial pressure of water is just the saturation pressure, we'll choose 0.1 atmosphere since that's pretty reasonable. This won't change, so that means that the partial pressure of air won't change. So if we start at 1.1 atmospheres, then we'll finish at 1.1 atmospheres. So what does this mean if we remove the water? Well, we could take a look at the ideal gas law for air. So for the ideal gas law for this air, it's just going to be the pressure of the air times the volume, and that's going to be equal to the moles, gas constant, temperature. We know temperature and gas constant are constant in this case, and the pressure is 1.1 atmosphere. So if we're decreasing the moles of air since we're removing them, that means that the volume must also decrease. We removed half the air, which means that we'll have half the initial volume that we did in the container. We can also write the partial pressure of water in terms of the ideal gas law. So we can say that the partial pressure of water times the volume of the container is going to be the moles of water times the gas constant times the temperature. And again, we know that the temperature and gas constant are constant in this case. And we know that the pressure of water is just the saturation pressure, which is constant as a function of the temperature. So as the volume decreases, we are also going to decrease the moles of water in the vapor phase. So the moles of water is just going to be half of the initial moles that we had to start with. So we're going to conclude that if we just remove air from the gas phase, then the water must condense, because we can't have a pressure in the system higher than the saturation pressure of water. And since we have the volume available for the water, we must also have the number of moles to have the same saturation pressure of water. And of course, if this were a non-ideal gas, the same ideas would apply.